Okay, so we were discussing redox reactions, and we have so far learned how to identify the reducing agents as well as the oxidizing agents. And we just did an example of calcium with two protons, giving you calcium ions and the hydrogen gas. So another example that I wanted to do here is 2Fe2 plus chlorine gives you 2Fe3 plus and 2Cl negative. So a couple of ways to see this. Like I said, more metallic a character is, it will have a tendency to lose electron. More non-metal like character, that will have a tendency to gain electrons. So you can see that Cl, which is more on the right side of the periodic table, should be your oxidizing agent. Oxidizing agent. And Fe, which is the metal, is going to be your reducing agent. So one is the placement of elements on the periodic table. Another way you can view is which is going through reduction, which is going through oxidation. So hopefully you can see Fe2 plus to Fe3 plus, that's an increase in oxidation number. So that automatically means that Fe2 plus is going through oxidation, and hence it's a reducing agent, so makes sense. On the other hand, Cl is going from 0 to -1. That's a decrease. That means that must be going through a reduction process, and hence it's going to be acting as an oxidizing agent. So please realize that you will find both the oxidizing agent as well as reducing agent both on the left hand side, the reactant side of the reaction. Now, I'm going to do a balancing of redox reaction, and I'm going to put two others as separate screencasts because they are going to be long, and this file will become too long then. So I'm going to put two separate examples of this method. It's a little bit different than what you know about balancing of reactions. Specifically, this is only for redox reactions. And the second thing you need to know is you essentially will need to balance out the oxidation as well as reduction components of the reaction, and then you go forward. So this sometimes also is referred to as the half reaction method, which allows you to focus transfer of electrons, and it's important when you're thinking about batteries, for example, or electrochemistry, because you need to find out what is the total electrons that get exchanged, or you want to determine the electrochemical cell, or you want to determine whether or not a certain reaction was feasible. So getting to know the number of electrons that are participating in that redox reaction becomes important. So like we say, redox, since it's a half reaction method, you would want to balance out the half oxidation reaction as well as half reduction reaction, and then simply add them back. So I'm going to go over one of the examples. The steps that you have to follow, these are pretty consistent, are given in blue. Usually if you have presence of oxygen and hydrogen, that does involve water, and so I have given those in black, so those will be total overall steps. But for the purpose of this course, we'll try to focus more on when we do not have water. Here the equation that I have given you is that zinc plus Ag plus gives you Zn2 plus silver. That is what the reaction is. Now, the first time you view it, you probably would think that the reaction is already balanced because you have one Ag and one Zn on both sides. And so what does that tell you? What does that indicate? Well, I want you to pay attention to the charge that you have. You have a one positive charge on the left hand side, you have two positive charges on the right hand side. So there is a problem. So the first things first, what you will do is you will split this redox reaction into the oxidation half reaction and the reduction half reaction. So Zn is giving you Zn2 plus, that must be the oxidation half reaction. On the other hand, silver Ag plus is gaining an electron to become silver metal, and so that must be the reduction half reaction. Notice we have one atom of each kind, so that part is balanced. What is not balanced is actually the number of electrons. So if you view the oxidation reaction, we have zinc giving you zinc ions and 2 electrons. Silver is gaining that electron to give you silver metal. So while the metal atoms and ions, those are equal, but if you compare the two equations, the second equation, which is the reduction half reaction, that has a 1 electron change, whereas the oxidation half reaction, that has a 2 electron change. So in any electrochemical redox reaction, the number of electrons that are exchanged are exactly the same. That means in order to equate the number of electrons, you need to multiply the reduction reaction by 2 and then simply add the two reactions. And that's what I'm doing in the last step. So reduction half reaction, I multiply by 2 and I'm going to add that to the zinc step. And so it will look like, upon addition, it will look like Zn, let's just type that down as well. It's going to look like Zn plus 2 Ag. Of course, we have 2 electrons here, plus 2 electrons, and they are giving you Zn2 plus, Zn2 plus, and I'm taking silver, which is solid, that's the reduction product, and of course I have the 2 electrons here as well, 2 electrons. And so hopefully you realize that this 2 electron right here on the left side is going to get cancelled with the other electron, and what remains, that means Zn plus 2 Ag plus, giving you Zn2 plus and then Ag. That will be your final balanced redox reaction. Now, the last 3 kinds of reactions that we'll discuss, the single replacement reaction, the combination reaction, and the decomposition reaction. So let's take a look at the single replacement reaction. Single replacement reaction will be a reaction where we will have an active metal which displaces another one. So in real life, I can compare that perhaps to a couple is dancing, and then let's say a hunk goes over and wants to dance, and so the more active metal, if you will, displaces the less active metal from that compound. So as an example, if you take iron nails and you put it in copper sulfate, the blue color, that bright blue color of copper sulfate, gets discharged over a period of time, and you see essentially like a black precipitate that gets generated. So what's happening is, this is the copper and the sulfate that were dancing, and Fe is the more active metal. So Fe is going to displace copper from its partner. And if you consider the opposite, that means the reverse reaction, that would not be feasible because copper is not strong enough to carry out that reaction. That means if the forward reaction is possible, then the backward reaction in this case is not going to be feasible. So in this series, in general, the most reactive metals are going to appear first, and the less reactive metals are going to appear later. Now we are going to revisit this in general chemistry too as well, but right now I'm just going to give you generic format of the series, according to which you can see that the representative metals, which are all the alkali metals and the alkaline earth metals, followed by aluminum, these are the top scorers. So let's call them representative metals. That means group 1 and group 2. Maybe in parentheses I'll write that as well. 1 or 2. These are the most active metals, followed by aluminum, followed by transition metals, and then comes hydrogen. And then hydrogen, which is usually taken as a standard to measure the reactivity against. Past that, we have the coinage metals. So copper, and silver and gold, those are all coinage metals. And notice gold is the last one in activity, so that should tell you something. No wonder gold jewelry is, it's pretty resistant to reaction. Or you can say that in earlier days, or even now, jewelry is made in gold because gold is going to remain gold. It's not going to react with air or water and change forms. No chemical reaction is going to take place. I have never in my life seen anybody wear something made of sodium. Well, guess what? It's going to cause a skin burn if somebody tries to do that, because sodium is so reactive. It's going to take the moisture from the skin. So realize single replacement is going to occur in a manner where the more active metal is going to displace the less active one. So let's say if I tell you that if you have test tube 1, which contains a metal, okay, let's say it contains metal A. Test tube 1 contains metal A, and that displaces B. Okay, so A displaces B, and B displaces C. B displaces C. But C can't displace A. C can't displace A. So how would you arrange them in an order that you provide a reactivity order essentially? So realize A is able to displace B. That means A is more powerful than B, and B displaces C. That means B is more powerful than C. C can't displace A, and that makes sense. C is much lesser than A, so it would not be able to displace A. On the other hand, A will be able to displace C as well. So the way I just wrote that is the order. So you could be given statements like these, and you have to essentially arrange them in the increasing or decreasing order of reactivity. Now, the last bit is combination reaction and decomposition reaction. Combination reaction is a reaction where two simpler substances are combined and they form a more complicated compound. So you'll begin with, let's say, something as simple as magnesium, okay, and let's say you burn it in oxygen, and it burns with a flash and it generates magnesium oxide. So you're going from simple elements to a complex compound. You will call this reaction combination reaction. Sometimes it is also referred to as synthesis reaction. A good way to identify that is you will see many reactants. And usually they will culminate in one product alone, only one product. The opposite of a combination reaction is going to be a decomposition reaction. So you're going to begin with one compound and it's going to break down into simpler compounds upon action by heat or light. So usually decomposition will require some kind of heat or light which will be used to trigger the reaction, and something like mercury oxide, for example, giving you mercury and oxygen gas. So you start with a complex thing, so you have one reactant, and you're going to get many products out of it. Many products. And usually on the arrow it will either say heat, so heat can be shown as the delta triangle, and I don't think I will be able to change the font here, but heat is shown as delta, and the Greek symbol delta. And sometimes you can even see h nu for light or some specific nanometers, so that tells you that there is a radiation that is associated.